All right, so let's take a quick look at how to use Cramer's rule to solve a linear system. So our first step is we need to make a coefficient matrix. So we will take note of our coefficients on our x terms, as well as the coefficients we have on our y terms. We'll pull those out and we will go ahead and put them into a matrix so that we can take the determinant. So we've got 6 and -3 as our coefficients on our x terms, and then -2 and 5. And we just preserve their layout as they appear in our system. And we'll go ahead and take the determinant now. So we will multiply 6 times 5, which is 30, minus our other product, which is -2 times -3, which is a +6. But we remember that in our determinant, we always subtract the difference. So we always take the difference of the two products. And so our determinant here is 30 minus 6, which is 24. Okay, so now that we've got our determinant, it's time to go ahead and solve our system. So we're going to use Cramer's rule to do that. Let's start off by looking for the x coordinate of our system. Since we have a non-zero determinant, right? Non-zero, woohoo, that means we can solve for an ordered pair. That means our system is consistent and independent. There will be one solution, and that's all we have to look for. So let's find it. We're looking for an ordered pair, looking for our x coordinate. So we're going to use a fraction to do that. Our numerator will be the determinant of the matrix, the coefficient matrix, in which the x coefficients are actually replaced with our constant terms from our original equation. So instead of 6, we'll write -16. And instead of -3, we'll write 16. And I know that might feel a little weird when you first do it, but since we're looking for the x, right, that's what we want, then we'll replace our x terms with our constant terms. That's just how Cramer's rule works. So we just have to be familiar with it and comfortable doing it. Okay, so that's our numerator, is the determinant of that new matrix. And the denominator is the non-zero determinant we originally found, which is 24. And that's our x coordinate. So we'll go ahead and determinate to find it. So we'll say, okay, -16 times 5. Okay, and that gives us -80 minus 16 times -2, which is -32, over 24. We'll simplify that. So we have -80 minus -32, which is +32. So that's a -48 over 24, which we can simplify to -2. So, all right, we've got one part of our ordered pair ready to go. And now we just need to find the y coordinate that goes with it. In order to do that, we're going to do the same thing that we did when we looked for x, except now, since we're looking for the y coordinate, and that's what we want to find, we're going to replace our y column of our coefficient matrix. So when I make my matrix, I'm putting the x coefficients back where they were, 6 and -3, because those come from my original. And now, instead of writing my y coefficients of -2 and 5, I'm going to use my constant terms, -16 and 16, since I'm replacing my y column with those. All right, and in the denominator, we have our original determinant that we found, 24. So now it's time to determinate. We go ahead and do that, and we end up with 6 times 16, which is 96, minus -3 times -16, which becomes +48. That's divided by 24. And when we subtract, we get 48 over 24, which we can simplify to 2. So there's our y coordinate. We've now got our solution. These two lines intersect at -2, 2. And you have a couple options for checking that solution. The first option is you can plug back in to both equations, or you could also graph them. And since these are given to you in standard form, you might want to use an app like Desmos to graph and prove to yourself that they do intersect at the point we found using Cramer's rule.